So let's continue looking at graphs of one-dimensional motion, but this time we're going to go in the opposite direction. So now let's say we're given an acceleration as a function of t. And so we're going to say, so we'll label 2, 4, 6, 8 in meters per second squared and time in seconds. So let's say, for example, we have something like, like a car that's starting up. So initially, maybe we hit the gas, and so for the first 4 seconds, we're increasing for the first 2 seconds we're increasing at 4 meters per second squared, and then we go at a constant velocity for a while. And then maybe there's like a deer in the road or something like that, so we have like a sharp change in our acceleration. That only has to last for a second, and then we're stopped. Maybe we're stopped, and then we continue on for a while, just kind of waiting, and then we start to speed up again. Okay. So now we can look at the velocity of this curve. Okay, so to find the velocity, so we have to know, again, we're doing an integral, so we could be starting anywhere. So let's say that we started from rest, so that our initial velocity is 0. Okay, but really this doesn't have to be true. We can start our velocity at anywhere, because remember, to go from velocity to acceleration, velocity is the integral of the acceleration with respect to time. So in this case, if we have a constant acceleration, that means we have the acceleration times the time plus our initial velocity. So we really have to define this when we start out. So we're going to define that we started out from rest. Okay, in this first period of time, we see that we had 4 meters per second squared in 2 seconds. And so the initial velocity is 4 meters per second squared times 2 seconds. So at the end of the time interval, we're going 8 meters per second. Okay, so we'll go 2, 4, 6, 8, 10. And so we're going at, so after 2 seconds, we're going to be at 8 meters per second. The acceleration's constant, so this is just a straight line. Now, of course, had the acceleration not been constant, if the acceleration was changing, then the velocity would also be changing. It wouldn't just be a straight line. But in this case, it was a constant acceleration, so we have, so it's just a straight line connecting our final velocity at this point. So here our velocity is 8 meters per second. Okay, and then we have several seconds where we're not increasing our velocity at all, and now we have a sharp deceleration, right? So now in 1 second, we're going to decrease our velocity. Let's see, for 2, 4, 6, 7, right? 2, 4, 6, and 7, right? So we're gonna, so in this next time interval, we go down 7 in 1 second. So now all of a sudden in the next second, we're going to be down all the way down to 1 meters per second, right? And so the way that we can see that again is remember that velocity is the area, an integral is the area under the curve. So here we had 8, right? That was the area of this one. In this one, the area is this is 7, but we're below the origin, right? So now our total velocity here at this point is 8 minus 7, and that gives us 1. Our velocity at this point, our velocity is constant again up until here, and now we increase. So now we go from at 4 meters a second in 2 seconds again, so this is another 8. So this is telling us that we're going to go up another 8 meters a second. Which would bring us to there in 2 seconds. So we didn't go to 8 meters per second, right? Because that would be this point. But we went up 8 meters per second from where we are. So we have 8 minus 7 plus 8 is equal to 9 meters per second, and that's our velocity at this point. Okay? So similarly, let's look, we can do the same thing if we're given velocity in meters per second in time, and we're looking for our position. So, so again, we'll do our velocity is 2, 4, 6, 8, and 10, and time is going to be in 1 second again. And so now we're going to say we start from rest, and now let's say that in 2 seconds we increase to 4 meters a second. So now we have a velocity that's changing, right? And then let's say we're constant at 4 meters a second for a while, and then let's say we quickly stop, and so we stop moving for a little while, and then we slowly speed up again, and then we stop, and then let's say we slowly start moving backwards for a while. Okay, and then we want to find out where we end up. So we'll stop again, and we'll find out where we are at this time. Okay. So let's see how that would look. So if we look at position now as a function of time, and we'll do 2, 4, 6, 8, 10. So now we see that in the first 2 seconds we increased. We increased up to 4. So again, if we look at the area of this is going to be 2 seconds times 4, but divided by 2 because it's a triangle. So the area of this is 4. So we've gone 4 meters in 2 seconds. Okay, but there's a difference here. Our velocity in this case wasn't constant. It was linear. Right, and so we know that if we have something like x is equal to the integral of vt dt, then this is going to be 1/2 vt squared. So in other words, this is going to be parabolic, so we can expect our position curve to look something like this. Okay, and then in this next time interval, the velocity was constant at 4 meters a second for 2 seconds. So our area here is 8. So now that means that our position is going to increase by 8. Okay, so increasing by 8 means now by the time we get to this time, we're going to be up to 12 meters. This time the velocity was constant, so this is going to be a linear change in position. Okay, in this time interval we're not moving at all. We go up another 2 meters per second in 2 seconds. So we go up another 4. So that's actually going to put us all the way, that's going to put us all the way up here by the end of the time interval. So this is saying that we're at, let's see, 12, 14, 16. And let's see if that makes sense. So we have 4 plus 8 plus 4 is equal to 16 meters. So that's the position that we should be at this point in time. Okay, we're at 16 meters. Now the velocity we see went back sharply. So now we were going at minus 2 meters a second for 1, 2, 3, 4, 5 seconds. So this is 10 meters per second. So now we need to go. So now we need to go down back 10 meters. So now we should be at the end of this interval. We should be at 6. And again, it's a constant decrease in velocity. So we end up at 6 meters. And so the way you can tell is 4 plus 8 plus 4 is 16 minus 10 is equal to 6 meters. So that's our final position here. So you see that by taking the area of each of these blocks, we can find out what the position was. Now let's say instead of finding our final position, we wanted to find the total distance traveled. Okay, that's going to be the same thing, only now we have 4 plus 8 plus 4 plus 10, we're adding this 10 instead of subtracting it because we want to know what our distance traveled was. And so 4 plus 8 plus 4 plus 10 is going to be, let's see, 8, 12, 16, 26 meters. So our displacement was 6 meters. Our total distance traveled was 26. And so that's how you solve problems like this. And so, again, on your exam, you're almost definitely going to be asked a question where you have to do some type of differential curve. So you're going to have to do like we did in the last video. And then you'll also have to do an integral graph and give something like the total, the final position and the displacement and all that. So make sure you do these problems in your book. Make sure you do them in Halliday Walker Resnick, and ask me in class if you have any questions on it.